I'll introduce our next speaker. Our next speaker is going to talk to us via Zoom. And this is Rajeev Mshra from HPE, talking about the impact of data loader caching on Lustre, a hybrid I/O approach. Short bio. So Rajeev is a software engineer at HPE, working in the HPC organization. He recently joined the Lustre team and is thoroughly enjoying analyzing the file system, exploring performance characteristics, and going deeper into insights into the interfaces. So let's sit back and learn from Rajeev. Thank you.
Good afternoon, everyone. It's my pleasure to be presenting this. I'm not there, but I'm taking it over Zoom. So this paper I want to present is basically related to how the ML perf workload IO patterns are and what impact hybrid IO can make on this. So my agenda will be like just to zoom through the ML perf storage, workload options we have on the ML perf, hybrid IO, just a hint of that, and then go deep into workload data loader, then it's IO profile, deep dive, and then I will talk about the uh, test I did with the hybrid and non-hybrid and what the results were. So this is in continuation of my colleague did a presentation at LUG explaining about the MLPerf, and he has gone in depth about MLPerf, how it works. But here I'm just scanning it like what MLPerf is. Basically, MLPerf is the performance benchmark for the storage they have. And how they do is basically they load the data and they emulate the GPUs. They currently support A100 and H100, and both of them are like basically fine-tuned into the code. They have, as I said, it is basically an emulation of the GPUs now, so you don't need all those expensive GPUs on the system to run these. So I will go next to the workload options we have. So workload options, we have three workload option. One is Unit 3D, there is ResNet 50 and CosmoFlow. Unit 3D is very heavy on IO, and we will see that. And the data loader, it uses it PyTorch, and ResNet 50 and CosmoFlow, they uses TensorFlow, and we will go into detail when we go talk about these workload. So by Unit 3D, I said it's mostly for medical image, like segmentation it does, and for ResNet 50, it basically classifies the image, and CosmoFlow is like it has huge data images, which basically it tries to find out the structure in that. And all these data, when we use MLPerf, they are not the real data, but they are a synthetic one. So that is another thing which is important in the MLPerf. It is all generated data that's not, you don't have to download, you just can use it. So now I will go into hybrid IO and what thought process I had before I jumped into this experiment of hybrid IO and MLPerf workload. So hybrid IO, as you know, like it is basically a direct IO into the buffer of the application calling the uh, read write or whatever. So if read is called, the data is read from it's a direct IO, and we have two tunable there. One is like read threshold and write threshold, and when you set those threshold, it basically, when you hit that threshold, it will do a direct IO. So for example, if you set it to 1K, then any IO on read beyond 1K or 1K will be treated as direct IO. And preliminary assumption we had was basically all these workload, they might be doing caching and they do random read. And also we were very much impressed by the GDS direct IO approach. And we were thinking like, in GDS, like you can directly write into the GPU memory the data from the disk into the memory, and it saves time. So we were thinking, if we are doing this approach and application is doing caching, we will save a lot of time when we run this workload. And now I will jump on to IO profile. So in IO profile, what I did was I used two approach. One was BPF trace. So I was collecting BPF trace uh, when these workload were running. And I had another tool, Darshan, which basically gives a profile of the workload in terms of whether it's sequential, what kind of speed it is, like basically all the throughput and everything. And unfortunately, that tool didn't work for me for Unit 3D, or I will tell you to be precise, Python, PyTorch, I was not able to work it, but with TensorFlow, it worked and it gave all the data. So I will go ahead with the Unit 3D. So I collected Unit 3 data, and Unit 3 data, when I collected, you can run workload with epoch 1. That means the when the data will be training will be happening only one time, it will go through the data. And if you set epoch to 2, it will 2 time, and it will do 5 time, and likewise, and then it will eventually show you the result. So what I did the plot of uh, so first I found out that these are all read only in Unit 3D. And what I plotted is the time and the offset. And there were, like in this case, I created some 7,000 file, but I cannot show you the plot of all the seven. So I picked up one or two files, but the pattern was almost same. I have plotted time on the y-axis and offset on the x-axis. And then the second graph is I have plotted read size and time. And the third is basically the file descriptor and the time, any activity on that file descriptor, which was basically read in this case. And then fourth plot I plotted was to get an idea about how long the read is taking. So in this case, the fourth graph is duration is on the y-axis and time is on the x-axis. So first graph clearly shows that uh, the reads are sequential, and it is basically going in the incremental order of the offset. And what we see in the second graph is all the reads are 4 MB in this case. So the numbers may not match, because the thing is the numbers have been basically shrunk to fit the graph. So it is 4 MB megabyte read size was there. And the third graph shows uh, that the reads are spread evenly in the time it run. But the last graph shows that the duration of the read is basically it is taking long time to complete, because we see initially it completed very fast, but as the workload increases, the duration was uh, going basically uh, more on the y-axis up. So it was going. So this is the second file, which shows exactly the same, uh, uh, basically same kind of uh, profile. It's sequential, 4 Mbps, so 4 megabyte write, and duration is heavy when it is reading. So duration to complete the read is higher. So I will go now. So then I repeated this experiment with the uh, uh, epoch 5, and then it becomes very interesting. So when I do epoch 5, what I was thinking was basically the workload will not read, it will just read once, and it will not do reading again and again for the same file. So what we are seeing here is, so epoch 5 will do 5 iteration, and we are seeing the 5 iterations are there. And we are seeing that reads are happening again and again after each iteration. So that means definitely the application doesn't do a buffering. And what we see on the you can see that offset is increasing, and the read, when you see the size, is also 4 mbps for each of the 5 epoch run. And you will see that the uh, inclination of the line is not similar to epoch 1. And the reason for that is because it has been shrunk in the time. So it ran for the longer time. So epoch 1 ran for some duration, epoch 2 ran for some duration, epoch 3 ran for some duration. Therefore, you see the read bytes are also, uh, it's not a continuous line, but in the time, it is like a segment there. So you will see the same inference in the file descriptor and read, that how the reads are in the time, because file descriptor, if you see, and the time you see, the reads are like spread, how they are spread in all the 5. But interesting part was, most of the delay was like uh, normally in the if you see, when I'm seeing the showing you the screen on the screen, that duration is basically, this is average, but one of the file descriptor, which is 49, it has taken more time, and I don't have data to correlate why it was taking more time. uh, but it will be something interesting for the further experiment, like why some of the reads are taking more time, whether the cache was flushed or something else. We will have to check it. But the uh, but the IO profile remains the same for the uh, epoch 5 case also. And then I took another example from the another file, and you can see that it just repeated the same inferences of the other file, and the workload remained the same. Basically, the workload pattern, IO profile for the unit 3D remains the same. And you can see that it's heavy on IO, so duration to complete is slightly higher. And we will see the impact when I run with hybrid IO. Now I will go to Resness 50. And here I was able to run Darshan and BPF trace both and do the profiling. So you can see that the BPF trace, Darshan clearly shows that most of the IO is sequential, and uh, it is basically increasing in the order. So, and most of the operation is read. So this is a close-up view of like it's total, sequential, and consecutive. If you see the 3 bar, they are same. That means total is sequential also and consecutive also. So most of the IO, not most of the, almost 100% IO is basically sequential and consecutive. We can say that. So this proves from the BPF. Now we will go to BPF trace, because this I was not able to find out how the is it. I mean, how much time read is taking and all those things. So I went more detail into the BPF trace, and I read. I again started with the epoch 1, and here I had like files, some uh, almost around 5,000 range. I have taken files, and then I ran the test case with epoch 1. And epoch 1, again, it was just one cycle of the training happens with the ResNet data. But one thing I wanted to point out, the ResNet uh, files are in the size of 137 MB, and UNet 3D, their size was quite heavy, from 400 MB. It had some files in 400 MB, and some were very small, like 1 MB. So the spread of the size was uh, too much in UNet 3D. But in case of ResNet, the most of the file was 137 MB. And these are the hints we can use when we will have to do the performance, basically enhancement, like how the UNet 3 file size is and other things. So now coming back to ResNet Epoch 1 run, you can see that with the Epoch 1, they had 2 file descriptors open. And here the file descriptor 65, it started from the beginning, and it read, and then basically it then again started and read the complete file. So basically it started and it read the complete file, and same thing happened with the unit 3. Most of the files are read completely. I didn't see any partial read, but maybe there are there because uh, uh, I will have to write some analysis code to check all the 7,000 file, but most of the files were complete read. So now the another also, if we see the trend is same, uh, which is file descriptor 46 here. In this case, it started, it read some file, and then it basically read to some offset, and then again it started from the that offset to the. So it what it is showing is basically it is reading again sequential, and everything is sequential. But in case of, because ResNet is using TensorFlow uses pread to read it. So it provides offset and the size it want to read, and the offset and size of read was always incremental. In case of Unit 3D, which uses PyTorch, it was opening and L-seeking the file and then going to that offset and then reading it. So the read pattern was slightly different in the Unit 3D, the way they read it. So, but the pattern was same, basically sequential, but the way they were reading was. So here, the size of the read was 256K, as you can see it in the second graph with the time. There are two very, like two reads off the mark, but most of them is 256K. And when we see the read operation in term of time, you can see that it is all evenly spread. But the interesting part is, uh, you can see that duration it is taking is very less. In Unit 3D, we were always in the air here, like uh, somewhere the duration was quite heavy. So here in this case, we see that the duration is less. The reason for that is the file size, like the number of reads it is doing, maybe it is same, but the read size is 256K. So the pressure, the workload pressure is not as high as Unit 3D. So I will take another uh, file, which I just, it is similar to what we saw in the previous file, the sequential pattern, and read size is 256K, evenly spread, and duration is less. So they are not uh, that IO intensive. So that is the another thing I wanted to uh, get your attention on. So if it is an IO intensive case, then we will, so it will impact the results too much. And if it is not, then if it is compute intensive, then it will not be affecting too much. And we will see that when we go further. So this is now I ran with epoch 5, and you can see that number of file descriptor has increased. And each file descriptor is basically reading in sequence pattern, and we can take any file descriptor and we can see that, like for example, if we take this one, um, which is 44, it started from here, which is time here. Like if it started from here, and then like it came forward in the reading, and then it completed the read, and then it read the remaining portion. So it can read in any order, but it will be sequential. Like it has gone back and read the remaining portion. Like you can see that it is here to here. Like, oh, sorry. So it has gone back and read the 5. So similarly, like all the 5, uh, all the other threads are also doing the sequential read. And we can see that here also the 256K read is there, and all the file descriptors are marked. They are on the 256K line. And we can see that epoch 5, so they have run in the different time, uh, uh, and different file descriptors are busy on the different uh, so all these are shown here, how the access was. And we can see that here also the uh, duration, which is the completion of the read, is not that high as Unit 3D. And here I was running with some 50,000 or 47,000 kind of 47,000 files. And okay, so now we will, 1 minute. Okay, now we will go to, so 1 minute, I just skipped. So this is another file which shows the same IO profile. Now I will go to the second one. Okay. So this is now the another workload which I wanted to do as part of this experiment. So in this also, as we were using TensorFlow, I was able to use the CosmoFlow. And here it is saying, again, most of the workload is uh, uh, read only, but there was a write piece which was very small. I'm not sure what it was, but it was very small. You can see that. So I was basically write is here, which is very small. I didn't go into the detail what write is about, but most of the read, if you see, they are sequential, and some of the portion they are. Uh, Darshan is thinking it's not sequential or consecutive. So. Uh, it is basically the total is given here. So, uh, so they may be random. At this point, I don't know. And when I did the BPF profiling, this is the workload. So again, the Cosmoflow, I did the same epoch 1 I took, and you can see that uh, this is, it has two file descriptor. One did just one read, and the other one was sequential. And we can see in the time it is again like it was reading 256K. Most of them was 256K read. And it is not uh, what to say, it is not that IO intensive. And we can see that in this graph, and we will see it in the, oh sorry, okay. So we can see this in the other epoch also, that the pattern is same. It's not that IO intensive, and it's uh, basically it's lesser than the ResNet also. And the reason is the file size here was only 3 MB to 2.5 MB. So in Cosmoflow, the uh, file size is even lesser than the Unit 3D and ResNet. ResNet has 137 MB of the file size. And when we do the Epoch 5, we can see that the number of file descriptors have increased, and the reading is here like in mostly in the 256K, and there is another range which was lesser. And then we can see that the time duration is less. The read is taking less time, and there are few which are delayed, uh, but most of them, they are basically well below some nanosecond. And uh, uh, basically most of the read in this case also was 256K. So now going ahead, so 1 minute, wait. Okay. So as I said, so IO profile inferences were read size was 4 MB, sequential, consecutive, and it was IO intensive, Unit 3D, and ResNet was 256K, sequential, uh, and same was Cosmoflow was almost same, uh, and the IO burst was there. In case of Cosmoflow, I did see that graph. Uh, so all the IOs, they are very like sometime very IO intensive. They come in huge number. I don't know how the application reads the data, but sequential. But they come in. Uh, they just come with so much of read at some point of time. So then what I did, now the testing of hybrid started, because I was knowing that now application doesn't buffer, because we saw that in the read happening for the same offset. So I did the hybrid, and I was kind of sure that, it will not help me. And my assumptions were that it will help, may not go, but there is a catch here. The reason is uh, the workload when I tested, they were not doing checkpointing. So maybe the next version of MLPerf, whenever it is available, when they will start checkpointing and all those, the inferences may change. So when we did unit 3D with hybrid on and hybrid off, so unit 3 was the most IO intensive workload. And we can see that with hybrid off, it was actually performing, the utilization was very high, 91%, and samples it was processing was 35.46. But as soon as I turned on the hybrid IO, it basically dropped. So, and I was expecting that because unit 3D was very IO intensive, and I was seeing delays without hybrid turning on. So then I did with ResNet 50, and here the workload was like not that intensive. And when we did hybrid off and on, they remain the same. Basically, uh, in other words, to tell it, the environment I was running, maybe that 50,000 file was not putting that much of workload. That hybrid IO didn't, like the caching didn't play much of role because uh, the IOs were not that intensive. So the turning on hybrid IO didn't change any result, as we can see here. And then I did the test on, okay, I did the test on Cosmoflow. And in the Cosmoflow also, as the uh, uh, as the IO patterns were sequential and not that intensive, like not so many reads were going and files were small, the hybrid IO turning on and off didn't create much of impact. So, uh, so most of the learning was from the unit 3D. So what we did, uh, we tried monitoring unit 3D with uh, read ahead, and we see that when we did the tuning properly, that we were able to see uh, some improvement in the unit 3D workload performance. Then uh, we wanted to test it on non-folio on folio system, but all my testings were done on the non-folio system. So my assumptions are basically, if we go and do the testing with a folio system where the caching and other things are benefited from the cluster and kernel support, we may see a better performance with the read ahead tuning on the unit 3D. And uh, other observation was, as the workload was increasing, the misses were misses were lot in the read ahead. And uh, so we wanted to tune it further, but we didn't have conclusion as at what point it will be the best. We did the standard setting, and definitely read ahead was helping because of the sequential pattern and the pattern we have already seen. So moving forward, uh, we will have to find out a way, because these IOs are basically, they come in burst, and we need to optimize the read ahead so that it basically serves uh, uh, the best. It can auto tune for the AI kind of workload, because it knows that it may not reread, because we didn't see rereading. So maybe they can throw it. It is already there, but the tuning has to be done, and we will have to analyze those impact. And then uh, some like, I don't know if we can we may have to do more experiment on the fast path, if we can somehow make Lustre better with the AI workload and the fast path, like we do cache it somehow, knowing that this is a AI workload, and depending on the pattern that uh, uh, we create a fast path for the AI workload. And folio will definitely help, and I don't have data for that. And uh, if we can come up with some mechanism when the IO burst is happening, and we can handle it efficiently. I don't have idea how to do that, but this is some of the points which came in my mind when I was doing the testing, and I wanted to bring it here. So those are my basically moving forward kind of uh, things we can do in the future. So inference, you know, uh, which I made after doing this experiment, is hybrid. perform similar if the IO workload is not heavy, but uh, BIO performs even better in case uh, of these heavy workload, and uh, it is because of the sequential nature of the workload. So that's all from my side. Thank you. I really appreciate you all listening to it. So let me know if you have any questions.
Do we have any questions for our speaker?
Hello, I have a question. Do you see any performance impact when you are doing profiling with BPF trace? I mean,
Yeah. So so when I did the BPF trace, I was not collecting the performance number, and BPF trace heavily impacts the performance for sure, because I did see 10% drop, but the performance number I gave, it was without BPF trace. So that was a normal system tune, and the profiling was done just to get the idea on the workload. Yeah.
got it. Thank you.
Other questions? I have one actually, Rajeev, but maybe it's more a question for Andreas. So do you do you think the upcoming hybrid I/O, patches from Patrick Farrell will help with all of that? And do you have any idea if it's?
So I don't have idea on when the patches will come, but it will be interesting when so one thing I wanted to make sure here. So all these number I took was for the worst case. Like when I say worst case, so hybrid IO is both for direct IO and buffered IO. Yeah. So I was knowing that the read size is 4 MB, so I was setting the read threshold to lesser. Okay, and making sure that everything is DIO. So it will be interesting, like when the system is running and we tune it, like if the workload is having random read size, like for example 1 to 4 MB, it has spread evenly, then it will be interesting to see if the combination of buffered IO and the direct IO will help or not. Because these so other thing I want to point out is this is all simulated workload. It will be interesting to run the real unit 3D and uh, all the, like, Cosmoflow, if they follow the same kind of pattern. Hopefully they will, because MLPerf has been designed to emulate the same thing. But it will be interesting to run the workload and see it. But it will have more uh, uh, more kind of impact hybrid IO once the checkpoint also starts coming. Because in checkpoint, what will happen, the workload will be checkpointed, and that time they will do a heavy write, and writing directly into the disk will be interesting. But I'm not sure on the release time. That Andreas will be able to answer, so I will not be able to answer that.
So, I mean, Patrick is working on hybrid IO, and one of the nice things about it is that the there's tunables to let this be semi-dynamic in terms of when you cut over from buffered to direct IO. And I do have a graph in my presentation that shows just recaps a little bit about how that works. But if that can be tuned by client type, or it can be potentially even dynamic at runtime, depending on what is the latency of these direct IOs versus how quickly the buffered IO is writing. But I mean, the expectation is, and if you see the graphs, anything that's if I remember correctly, I think writes cut over at 1 megabyte. No, maybe writes cut over at 4 megabytes and reads at 1 megabyte, something like that. And so we tried to find the balance between the best behavior points of each type of IO. And the good thing is you don't have to change the applications to get benefit from that, right? They just have to do decent size I/O to the file system so that they can get the
So
best performance.
I have a question on hybrid I/O. I don't know. Is it Patrick answering the question or someone else?
Or it's Andreas.
Andres, okay. So the question is like the GDS part of the testing. Like this was not. This is all emulated, yeah. So will it be different if we do on the GDS, basically where the GDS is available and we do hybrid I/O? Will it make any difference?
Well, GDS has to do everything direct, right? And so
Yes.
there won't be any opportunity to use hybrid I/O because the way GDS is implemented, since it's sending memory directly from the GPUs and the clients don't have any access, the CPU doesn't have any access to the GPU memory. In that case, we can't do anything like buffered the GDS writes, or conversely, for on the small writes, the threshold is only a single page, and so we can't automatically tune the GDS I/O sizes. I mean, that could be something that NVIDIA could do in their NVIO library to dynamically select between buffered versus direct writes. But as far as I know, everything that comes from GDS I/O is always direct, unless it's very small sub-page size.
Okay. Thank you. Thank you.
Do we have any other questions for our speaker? If not, let's give him a nice loud round of applause so we can hear. We are people in here. Thank you, Rajeev.
Thank you. I really enjoyed it. Thank you. We'll see you sometime soon. Thank you.